one of the things we're starting to creep up on is we've done some stuff about learning how to count atoms and name molecules and what makes up atoms and stuff, but now what we're really starting to get to is how things interact. What is the underlying mechanism that makes things react together? We got into it a little bit just recently with those reactions we were just doing, But basically what it comes down to is chemistry. If you want to sum up chemistry in the most simplest way, chemistry is all about what the electrons are doing. Basically about the electrons. And the protons and neutrons aren't important. But the reason things react with each other is all based on basically the electrons. Right? And this is something I'm going to tell you now, which will become a more important theme later, is basically atoms want to be happy. They want to be happy. And the thing that makes an atom happy are two things. Neutral charge, full shell. Now we haven't talked about shells yet, but you know what neutral charge is, right? And you've probably heard of full shells before, haven't you? In your previous class? Okay. So basically, there's only one type of element that has its cake if you need it to, and those are the noble gases. That's why they're non-reactive. They have a neutral charge and they have a full shell. They're like, I'm fine. Right? But every other element, it's a compromise. So if you remember, say in the case of sodium, sodium can be +1, right? Or it can be neutral. If sodium's +1, it's got a full shell. But it doesn't have a neutral charge. That's what taking on the +1 charge does, is gives it a full shell. But it gives up having a neutral charge. Now when sodium has a neutral charge, it doesn't have a full shell. So the problem is the rest of the elements on the periodic table can't do both things on their own. And that's why elements react. They react to try and figure that problem out. And so a lot of times what happens is maybe, as you guys know, in ionic substances, maybe a sodium, a +1, can come together with a -1 chlorine. Now since they're charged, they got full shells. But when they come together, they neutralize the charge out too. So they cooperate to get their cake and eat it too. Okay? That's like the underlying thing, what drives all chemical reactions, is trying to get this ability to have a neutral charge and a full shell. Now that's just looking down the way, a little further down the way. These things here, redox reactions, again, have all to do with the electrons. But this is the problem. I remember earlier this year, I showed you guys, one way to look up charges was, if you're group 1, you're +1, you're group 2, you're +2, group 13, you're +3, 15, -3, -2, -1. Ring a bell? But remember over here, there were some gray areas? And what were we looking at? We were looking at this number right here, which is not charged, called oxidation state. And I said it's kind of like charged, but kind of not. And so we're really going to get into oxidation state now. So let's say you're a sodium +1, or you're a chlorine -1. That guy lost an electron. Right? If you lose a negative, you become positive. This guy gained an electron. So this one clearly does not have the electron. This one clearly does have the electron. So it's kind of like this. Let's say I've got an electron here and I go, I'm going to give it to Gary. So now Gary has my electron. I lost the electron, that's me. There's Gary, he's got the electron. We've created what we call an ion. And that's a case when oxidation state is the exact same thing as charge. Now here's the difference though. You guys know that there's things called ions and ionic bonds. What's covalent bond all about?
It's one of the ions and oxygen sharing one.
Okay, so there's a sharing going on. So this is like me and Gary playing catch. So let's play catch, Gary. And if me and Gary are the same exact element, we're just going to play catch nice and even, right? Okay, but let's say we're different elements. And let's say I'm a hog. I'm a hog. So every time I get it, I hold on to it for a little bit, and then I give it to Gary, and I can give it right back. And then I go like this, and I hog it again, okay? Now the thing is that we both are getting the electron, aren't we? But I'm getting it more. It's not my electron, I just have it more often. And so in terms of oxidation state, we would say that I'm a -1. And we would say he is a +1. Even though he gets the electron some of the time, oxidation state says where is the electron most of the time. In the case of this one, it's always here, so most of the time it's with chlorine. But when we're sharing, it's whatever one gets it more often. Follow me? So what it really is not a reality, it's an accounting method. It's a way for chemists to assign where electrons spend most of their time. Not all of their time necessarily, sometimes all their time, but most of their time. Okay, now some reactions involve this exchange, and so we call these things redox reactions. So these are called oxidation reduction, is the long name for it. Oxidation reduction reactions. Or for short, we often call them redox. By the way, your next quiz, just looking ahead here, your next quiz will have 2 questions on it. One will take up the entire front, one will take up the entire back. So if you're somebody that has a tough time with long process, you've got to really work at this. Most of you guys, it's not going to be that tough. Most of you guys got a grip on this stuff already. So a lot of what we just did is going to be helpful in what we just did. So basically, these involve the exchange of electrons. Involve exchange of electrons. Got some Mountain Dew for Christmas.
Hey,
Okay, now, again, a lot of reactions have to do with exchange of electrons, but not always. Do you remember your single replacement reactions that we did? Just took the test on? And do you remember how one metal would have no charge, and then at the end it would have a charge? And one would have a charge and one wouldn't at the end? Those were redox reactions. There was an exchange of electrons going on. But do you remember your double replacement reactions where, and even the neutralization, where the ions just traded places? Those weren't redox reactions because the charges on the things did not change throughout the problem. So it's when the charges or the oxidation states change. Okay. Now there's a really neat way to remember how oxidation reduction reactions work. It's this: oil rig. Oil rig. It's like a nice little way to remember this. Some people use another one. I don't like the other one as much, so I'll just use this one. And basically what it stands for is oxidation involves loss and reduction involves tough to write like this, isn't it? Gain. Now I'm going to put down here in parentheses of electrons of electrons. So that's oil rig. What's the other one? I think the other one is, it's Leo says GER, which I think is stupid. I can remember oil rig better. It's like loss of electrons is oxidation, Leo. GER, gain of electrons is reduction. So if you like Leo says GER, you can do that, but I think oil rig works better. Okay. All right, so oxidation reduction, oil rig. All right. Now, in order to do oxidation reduction reactions, you got to understand what oxidation state is. Oxidation state. Sometimes called, I call it oxidation state, sometimes it's called oxidation number. They mean the same thing. So again, it's like I said before, it's an accounting method, just a way for us to keep track. counting method that assigns the electrons, or assigns electrons, I don't have to say B, that assigns electrons, it's freezing up. Go ahead.
No, it's in a what?
Oh, in accounting, it's supposed to say.
Oh.
I don't know what that word was that I just made up. An accounting method that assigns the electrons to the atom, or element, I'll just say atom, that has a greater attraction, to the electrons. Now later on down the line, we'll eventually talk about this concept called electronegativity. Remind me when if you ever see me blocking the screen. I notice that this blocks it sometimes. Later on, we'll get into something that describes how attractive atoms are towards electrons, something called electronegativity. But we can get to that later. For right now, what we're going to do is I'm going to give you a bunch of rules. You do have to memorize them. I know that's not fun, but that's the key to being able to do these problems, is knowing your oxidation states. Okay, so here are rules. And there's not many of them. And if you know the rules, for what is it? I got 5 rules here. If you know the 5 rules, then you can figure out for anything else that you don't have a rule for. So these 5 rules get it so anything else that becomes ambiguous becomes clear. Okay. All right, so here are the rules. Okay, 1. An atom of an element, oxidation state is 0. So for example, say we just have Na, it equals 0, or O2, each O equals 0. Maybe I'm going to make this different because that looks zeros and O's are confusing. Let me do N2, and then I'll say each N equals 0. That way we don't get into some ambiguousness there. So basically, if you're a lone element, you're not charged, and if you have no charge, you have a 0 oxidation state. Now the other thing is, see that N2? Okay, they're sharing electrons. There's 2 atoms that are sharing the electrons. The thing is who's going to win that tug of war? Nobody. It's like perfectly identical twins in a tug of war on the electrons. They're going to get it 50% of the time. You get what I'm saying? They're the same atom. They have the same properties. So nobody wins the tug of war. So we say nobody gets an extra electron. Nobody loses an electron. Okay. So atoms of an element, 0. 2, a monoatomic ion. Is equal to charge. We do it like this, just to stay consistent. So is equal to 0 is equal to charge. So what I changed here is I put there's an equal sign, so it equals 0. So here's an equal sign, it equals charge. There's my example of how they equal 0. Now I'll give you an example of how they equal 0. So example, let's say I have Na plus